Example 5, we have to find and solve the indicial equation for another differential equation and see what the roots are and determine which roots would lead to a valid solution. So let's go ahead and see how that one works out. Again, we start with the same exact guess as before. That's y is equal to the sum from n equals 0, an x to the n. And since we're using series solutions around regular singular points, we're going to jack that up to x to the n plus r. And let's look at the different terms that we're going to have to study here. We're going to have a 3y here, so I'll go ahead and figure out that 3y is just the sum from n equals 0 of 3an x to the n plus r. And then we're going to have an x times y. So x times y is the sum from n equals 0. That just bumps it up by a power of x, so an x to the n plus r plus 1. And now let's figure out y prime. Y prime is the sum, again, from n equals 0 of n plus r times an times x to the n plus r, and, x to the n plus r minus 1. And we're going to have to deal with 3x y prime and x squared y prime. So let me go ahead and work those out. 3x y prime is the sum, actually that's going to be negative, so I'll go ahead and include that negative. Negative 3x y prime would be, I'll put the negative inside the series, n equals 0 to infinity of negative 3 n plus r a sub n. Now x will bump up the power of x to x to the n plus r. X to the n plus r. And I'll also have to deal with a negative x squared y prime. So negative x squared y prime would be the sum from n equals 0 of negative n plus r an. Now the x squared is going to bump it up from x to the n plus r minus 1 to x to the n plus r plus 1. So that's our negative x squared y prime. And finally, we've got a y double prime, so let me calculate that. Y double prime is the sum from n equals 0 of n plus r, and then we've got a second derivative here, so I'll go n plus r minus 1, an times x to the n plus r minus 2. But we're going to have to deal with x squared y double prime, so we'll go ahead and multiply that by x squared. So x squared y double prime is the sum from n equals 0 of n plus r times n plus r minus 1, an, and now the power gets bumped up to x to the n plus r. It was n plus r minus 2 before, but we multiplied by x squared, so it's x to the n plus r. So if we look at all these different series that we have to combine, remember there's a two-step procedure to combining series. The first step is to match exponents. So we want all of those series to be in terms of x to the n plus r. And the second step will be to match indices, starting indices. Of course, we'll only get to that after we match the exponents. So we'll want the starting index everywhere to be the same. So we'll see what that has to be after we match the exponents. When I look at all these different series, I've got x to the n plus r here. That looks pretty good. My xy has x to the n plus r plus 1. And so I'd like to lower that down to be x to the n plus r. Remember, the way you do that is you raise the starting index and correspondingly lower the n's in the formula. So I'm going to go minus 1 on the n's in the formula, plus 1 on the starting index, and so I'll get the sum from n equals 1. Now I got to lower the n's in the formula, so a n minus 1 x to the n plus r, n plus r. And now let's look at y. My 3xy prime looks pretty good. I've got x to the n plus r there. That's looking good. But my x squared y prime has an x to the n plus r plus 1, so I've got to fix that one. Fix it the same way. I want to lower that n by 1, which means I have to raise that n by 1. So let me go ahead and do that. I have the sum at n equals 1. Now I've got to lower all of these n's, so minus n plus r minus 1, a n minus 1, and now I can lower the exponent, x to the n plus r. And finally, when I look at y double prime, my x squared y double prime, that's got an x to the n plus r. That's pretty good. So I've got this series, I've got this series, I've got this series, this series, and this series. All of them are now at x to the n plus r, so I've matched my exponents on all of them. The next step is to match my starting indices, which means I have to look at each one of these. I've got n equals 0 here, n equals 1, n equals 0, n equals 1, and n equals 0. I'm going to match them all up at the highest one, which is n equals 1. So that means for all the n equals 0 ones, I'm going to pull out one term. So I'm going to pull out the n equals 0 term. So let's go ahead and start here. The n equals 0 term here is 3a0 x to the r. And so that was my n equals 0. And now I have the sum from n equals 1 of 3an x to the n plus r. This one's already okay because it already starts at n equals 1. This one starts at n equals 0, so I'm going to pull out the n equals 0 term, which is minus 3 n equals 0, so 3r a 0 x to the r. And then I can go ahead and write the rest of the series, minus 3n plus r a n x to the n plus r. And I can start that at n equals 1 because I pulled out the n equals 0 term. This one's already okay because it starts at n equals 1. This one is not because it starts at n equals 0. So I got to pull out the n equals 0 term. Excuse me. Pull out the n equals 0 term gives me just r times n equals 0, so r minus 1 times a0 x to the n equals 0, so it's x to the r. And then I'll have the sum from n equals 1 of the rest of it, which I'm not going to bother to write because I'm running out of room there. And then I have to combine all of these series. So let me just indicate which of the series I have to combine. I have to combine that and that and that and that and this. And let's see how that plays out. I'm going to write all the extra stuff on the outside first. So I notice that all these extra terms, there's one, and there's one. All of those have an a naught times x to the r. A naught times x to the r. And now let's see what I have multiplied by that. That's 3. That's coming from here. This gives us a minus 3r. And then this gives us a plus r times r minus 1. And the other terms will all be the sum from n equals 1. And they all have an x to the n plus r, so there'll be an x to the n plus r on all of those. And I'm not even going to bother to write down what the coefficient is, because it would be collecting a lot of messy terms. There's a good chance I'd make a mistake doing that. So I'm just going to leave that open right now. And the reason I'm not going to bother is because of what the problem's asking me. The problem is just asking me to find and solve the indicial equation, and the indicial equation comes from this opening term right here. So this gives me the indicial equation. So we're going to find that, we're going to solve it, and we're going to see which values of r would lead to a valid solution. So let's keep going with that on the next page. The equation that we had right at the end of the previous page was 3 minus 3r plus r times r minus 1 times a naught times, well, that was the coefficient of x to the r, plus some stuff starting with n equals 1 times x to the n plus r plus 1 equals 0. So the x to the r term tells us that its coefficient must be 0, tells us that 3 minus 3r plus r times r minus 1 all times a naught is equal to 0. Now remember, an assumption we made for all of these regular singular points was that a naught is not equal to 0. So we always assume that a naught is not equal to 0. That means that the other part here must be 0. So we get 3 minus 3r plus r times r minus 1 is equal to 0. So that's the indicial equation. That's the indicial equation right there. But we're also asked to solve that, and we'll go ahead and solve that. It should be a pretty easy quadratic polynomial. In fact, if we multiply it out, we get 3 minus 3r plus r squared minus r is equal to 0. So r squared minus 4r plus 3 is equal to 0. And if we factor that, that's r minus 1 times r minus 3 is equal to 0. So r is equal to 1 and 3. So we get two roots of the indicial equation, and the problem asks us to determine which roots would lead to a valid solution. And the important thing here, if you remember back to the very beginning, the lesson overview, there's an important distinction when the two roots differ by an integer. So here, 3 minus 1 is 2, and 2 is an integer. So the difference between the two roots is an integer. So since the roots differ by an integer, remember what I said at the beginning of the lesson in the lesson overview. If they do differ by an integer, you can only make a solution out of the larger root. Only the larger root r equals 3 would lead to a valid solution. So that's the end of what this example was asking us to do. But if you wanted to keep going and finish solving this differential equation, what you would do is you'd have to take r equals 3 and plug that back into this differential equation, get a recurrence relation, and then build up your series solution one coefficient at a time. It's rather messy, and so I'm not going to do it, but that's how you would keep proceeding here, is with r equals 3. So let me remind you exactly how we got to this stage. We started out with our generic guess, y is equal to the sum from n equals 0 to infinity of an x to the n plus r. We figured out y prime and y double prime, and then we multiplied y prime and y double prime by the various coefficients here, x squared, 3x, x plus 3, and so on. And we plugged those terms into, we got these big series, and then when we got all these different series, the first thing we did was we tried to match exponents. X to the n plus r. And then we tried to match starting indices. Now with these series, some of them started at n equals 0 and some of them started at n equals 1. So what we did was we took the n equals 0 series and we pulled out the n equals 0 terms, and we started the series at n equals 1. So they all matched at n equals 1. But then these n equals 0 terms, those were the terms that gave us this extra equation out here. So that came from the n equals 0 terms. And then with those terms, we found the indicial equation. And that turned out to be a quadratic polynomial. That was using the fact that a naught is non-zero. So that turned out to be a quadratic polynomial, which was pretty easy to simplify, to factor, and then solve into r equals 1 and 3. So we get these two roots, and we check their difference, meaning we subtract them. We notice that their difference is an integer. The difference between the two is a whole number. And we had a rule from the beginning of the lesson that if the roots differ by an integer, you're only allowed to use the larger one to get a solution. So the way you go ahead and finish this differential equation is you take that larger root, r equals 3, plug it back into the recurrence relation, and start solving for your coefficients one at a time. So that's the end of this lecture on regular singular points as part of the series Solutions of Differential Equations. My name is Will Murray, and you're watching Educator.com. Thanks for joining us.